Okay, so welcome to our last class, our last new material class. The only thing that we have left to do is what is called the chi-square goodness of fit test, which we started chapter 24 last time. And we did the chi-square independence test, which used one technique involving matrices, was quite time consuming. This one does not use matrices. It has a different technique. It's a lot faster. And all the stuff you can do in a calculator still. So what is the chi-square goodness of fit test? Thank you, thank you. Thank you, I appreciate it. The chi-square goodness of fit test is the following situation. Suppose I come along and I tell you, for example, that I have a fair die. I whittled this die out of wood and I want to use it for a game. I believe that all numbers are equally likely. Well, if all numbers are equally likely, then that means that the probability of getting a 1, a 2, a 3, a 4, a 5, and a 6 are all equal and are all equal to 1 over 6, correct? I did not do attendance, but I'll do that later. I just completely forgot. Well, if I want to test to see whether or not the coin truly is fair, what should I do? If I want to test, I should test it. That's so brilliant. But can you be a little more specific as to how? Hey, as to how I have to test it. You roll it. How many times? 1? Okay, you roll it lots of times. And then you calculate your observed frequency or your observed proportion of each of the numbers. And then we want to compare our observations to our expectations if the model that we believe is appropriate is correct. So we are testing to see how good the data fits the model. Those of you who are grammatically correct might want to call it a wellness of fit test, but then the word that we use is a goodness of fit test. So what we do is we compare two things. We compare our observations to our expectations. And then all we do is go to our calculator, plug in a few numbers, pop out an answer, and come to our conclusion. So let's do, all we need is one example. And we can start the review. And our one example from chapter 24 will be the following. Okay, so this is example 24.8 on page 546. It says, births are not evenly distributed across the days of the week. Fewer babies are born on Saturday and Sunday than on other days. Now, why should this be the case? Even before we get to the math. I mean, babies, pregnancies, births, as far as I know, there's no knowledge. Oh, it's the weekend. Let's not get birth today or tomorrow. So why should it be that the data supports the fact that fewer births occur on Saturdays and Sundays than Monday through Fridays? What would be a reason for that? Well, no, I'm not saying the total number is less. I'm saying the number per day on Saturday and Sunday is less, significantly so, than the number per day on Monday, Tuesday, Wednesday, Thursday, Friday. Yeah. Yeah, but how does the baby, I mean, births come when they come, don't they? I mean, I assume, right? That's just the way it works, right? So the babies don't know, hey, it's the weekend, you know, hey, you know, so yeah. What?
Sometimes like how like your mind tells you like, oh, it's the weekend, party time. So maybe the baby.
So the baby is planning on party time.
Yeah, that's why they kick. Like trying to.
That's why they kick, because they're partying inside the womb.
Yeah, you don't know.
You say yeah like it's a sure thing.
Well, have you been inside a womb?
I have not myself, no.
Exactly.
I have
You
not.
wouldn't know, right?
That's true. I should not deride your comment because you might very well be correct. You're right. They might be getting drunk. Yes. Another answer possibly?
Maybe it's like there's not enough workers or something to like help get the baby out.
Did not love what?
They don't have enough like people working to help get the baby out.
No, I don't think that's the case. Babies, they don't just say, oh, can you wait an hour or so? Because so there you go. Nowadays, I'm not saying all births. I don't even know the statistics for how many births, but a significant amount of births are induced. They're scheduled in advance. Okay, the natural process is escalated. So if you're going to induce a birth, then why induce it on the weekends when you're going to be playing golf or something like that? You should induce it during the week, Monday through Friday. Yes. Not the babies, the doctors. They give you a thing and things happen and things go. I know. So the question is, are births evenly distributed, even with this understanding that inducements occur or not? Well, we'll do a test. So, no, a chi-square goodness of fit test. So, what we're going to do is we are going to take our data. We have Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. And in this particular experiment, there were 140 births taken at some hospital. And the observed values were 13, 23, 24, 20, 27. I think I skipped a number. 13, 23, 24, 20. Oh, I wrote Sunday twice. That doesn't make any sense. Okay. So Thursday is 27, 18, and 15. So these are the observed values. There were 140 in total. And these are our observations. Now, numerically, it certainly seems that Sunday and Saturday have fewer births than the other days of the week. But as always in statistics, we now know we have a way of looking at the world statistically, which says that we don't just look at the numbers, but we recognize that these are just samples, and samples are always going to have some chance variation to them. So we want to make sure our numbers are far enough away from what we expect to conclude that the result is significant. So we have to compare it to our expected values. Now, we are checking to see whether or not the data fits a uniform model. A uniform model is one in which we expect to have the same number of births every day, because why should one day be different than any other day? If there's a total of 140 births, then how many do we expect to have every day? 20. 140 divided by 7. So we expect to have 20 every day. It's a lot of babies, you said? Well, there's something like what, 8 billion people in the world, and all of them at one point were babies. So, and it really is crazy. It's I know, it's nuts.
We were all babies at the same time.
No, we weren't.
Oh yeah, well, not everyone, because it's some people are older, but like. technically, we were all babies at the same time.
Sure. So the question, sorry,
I can be Joseph's brother.
so we take out our calculator. And I would like you to guess where we go for this one. It's not a t-test. You've already asked. I've already told you what kind of test it is. It's a chi-square. Well, we will, before we put in the data, I want us to see how to put it in. So go to the appropriate test. Where do we go? So tell me the buttons that I press to get there. Stat, test, or the one that's listed as chi-squared GOF test, chi-squared goodness of fit test. And it asks for basically three things.
How do you know to choose between the chi-square test and the chi-square goodness of fit test?
Well, if it's in the test of independence, it's the chi-squared. If it's the goodness of fit test, then it's the chi-squared GOF test.
Like just say there was only the observation, like stat.
The GOF test is always observations and expectations. The independence test is when you two-way tables from chapter 6 or 4. So there are two different approaches. Now, if you look at what it's asking for, the first things it asks for are the observed and the expected. And what is next to the observed and the expected?
Yeah. AB.
Not AB, that's the wrong test. L1 and L2. So what I'd like you to do is quit out of this altogether. Hit stat again. And this time hit edit. And in list 1, what are you going to put? You're observed. So 13, 23, 24, huh?
2026. That's right.
What?
Thanks.
I haven't done it yet.
Wait, bro.
27, 18, 15, and L2, 20, 20, 20, 20, 20, 20, 20. And now let's go back to the test. Now that the data is in, let's go back to the test. But it asks for one more thing, which we have to give it. The degrees of freedom. The degrees of freedom is equal to the. Thank you. Thanks. The degrees of freedom is equal to the number of entries minus 1, n minus 1. So in our case, there are 6 degrees of freedom, and then we calculate.
Is there any time going to be an exception to that rule for degrees of freedom?
Well, yeah, the two-way table is rows minus 1 times columns minus 1. It's a whole different formula.
Oh.
Yeah.
What's the CNT-RB?
Those are the contributions. The chi-squared is essentially a sum. If you remember, I think maybe I didn't give it to you. The chi-squared formula is a sum of the ith observed minus the ith expected squared divided by the ith expected.
Hello.
Hey, how are you, Sarah?
I'm good. How are you?
So for example, let's look at the first contribution to this value. What's the first observed? 13. What's the first expected? 13 minus 20 squared divided by 20 is 49 over 20 plus something. And if you look at the first contribution there in the bottom, 2.45 should be what 49 over 20 is equal to. So the contributions in the bottom are just the specific values telling you how they came up with the chi-squared of 7.6. The p-value, which at the end of the day is the one and only thing we care about to make our final conclusion, is what? 0.269, which is high.
You failed to reject.
It's a high p-value. We failed to reject. We let it fly, which means there's not enough data to reject the null hypothesis. There's not enough data to say that births are not uniformly distributed, even with inducements occurring. Well, the p-value is high. We do not reject the null hypothesis, but you have to put in the context of the problem. On the final, they're oftentimes going to say, come to a conclusion in the context of the problem. Just writing, I reject the null hypothesis says nothing about the situation.
Would write with the data given,
With the data provided, yeah,
I would not reject the null hypothesis
which is,
that babies are more likely to be born.
well, that's not specifically what it is. It's that the null hypothesis says that they're equally likely to be born every day of the week. Okay, so it's a nuance, but you're going further than what we're saying. The null hypothesis says they're all equal. The alternative says they're not all equal. Not all being equal does not mean they're all different. I can have 5 equal and 2 be different, and that's not all equal,
Also,
right? So there's a lot of possible ways to reject the null hypothesis. And in a more advanced course, you'd have a follow-up. Say, okay, now that we know that the null hypothesis is false, can we get more specific and say which part of the null hypothesis is false? But for us, we're not doing that. It's either you reject the null hypothesis that the model fits the data, or you do not reject the null hypothesis.
what would we say?
I would say the data supports the fact that births are uniform across the week. Something as simple as that is all I need to say.
Would you say it supports the fact?
Yeah, I think it's a fact, yeah. We're not saying the fact is true. I mean, I don't know, the word fact,
The claim?
the claim, that's a better word. Okay, because the word fact is very specific for truthful statements. So the claim is really better. So just to be specific, the null hypothesis is claiming that the proportion of the first equals the proportion of the second equals all the way through to the proportion of the seventh, that they're all equal. And the alternative is that PI does not equal PJ for some I not equal to J. That would be a way I might write it mathematically. But even in words, you can just say 2 of them aren't equal. At least 2 of them are not equal. Something like that. Okay, and that takes us to the end. And that's it. We have finished the curriculum for the course. So I'm going to pause the recording. All right, so we're back. Okay, so Math 140B Final Exam Study Guide. If you have some way of accessing Canvas, you can load up the file so you can go along with me. I would certainly recommend it rather than just listening, nodding your head and smiling. I'm sure you've all had the experience of seeing somebody do a problem, feeling like you completely understand how to do it, and then 5 minutes later trying to do it yourself and realizing that you don't even know where to start. Okay, so it's very easy to fall into the trap of thinking that because I give you the answer and it makes sense when I say it, or somebody else says it, that you understand it. So every question, I'm going to give a couple seconds for everyone to write down what you think the answer is. I'm not going to compile your answers, but I want you to write down what you think the answer is, so you'll know for yourself whether you would have gotten it right or wrong. And if you got it wrong, then you know what to focus on. And if you get it right, then you know what to not spend so much time on. Sorry? It's on Canvas under Files, and it's Math 140B Final Exam Study Guide. So question 1. First of all, does everyone here able to look at it, or do I have to read the questions? Is there anyone here who has no access to this and therefore needs to see it and needs me to say it? On Files. Okay, so number 1. I'll give you 15 seconds. Number 1. Okay. You should know what, of course, skewed right means. You should know how that affects the mean, how that affects the median. And you should know whether or not for skewed data, you'd prefer to use the mean versus the median. So just answering the question is not enough. There's actually a lot of information that this question is referencing. But either way, what's the answer? C is correct. Question 2. Question says, for the data shown in the graph below, which of the following would be the best measure of the typical amount of money spent weekly on eating out? First, 2 of those answers can't possibly be correct because they're not even referring to a measure of center. They're referring to a measure of spread, which the question is not asking for. Which 2 of those should I immediately throw away? IQR and standard deviation. So even if you didn't know if it's the mean or the median, at least, guessing 1 and 2 is better than guessing 1 and 4. But what is it, A or C? The answer is A. This is skewed data. And with skewed data, we always take the median. It's really no different than the first question. Well, it is different, but for skewed data, we prefer the median versus the mean. You guys recall that vaguely?
Yeah.
Okay, so if you got it wrong, something to think about. Question 3. So which operation on the calculator am I using for this problem? Inverse norm. I want the lightest 4%. So what value cuts off the lightest 4%? D 2510. You do 0.04 to the left, 4% to the left with a mean of 3350 and a standard deviation of 480. Yes? Not a tests. Inverse norm.
Why don't you do it to the right on the of the tail?
That's the highest 4%. We want the lightest 4%,
Oh, so the lightest one, oh, I see.
right? I mean, a scale has the smaller numbers on the left, the bigger numbers on the right. So if you want the smallest 4%, that's going to be on the left.
So if they want the highest percent, it would be the, in what case would you use the middle?
In what case would I use the middle?
What kind of question would they ask for, you have to use the middle, center?
I mean, we want to throw away the top 2% and the bottom 2%. So we want to use the middle 96%, something like that. I mean, there's many ways you can do it. All right, question 4. Huh? Which one? Inverse norm, 0.04, paste. What's our answer for number 4?
See,
Answer is C. The correlation is 0, then they have nothing to do with each other. So why would one tend to indicate anything about the other? So C, good researchers are just as likely to be highly rated teachers as they are to be low rated teachers. And the same thing for poor research. There's no connection between them. Does that make sense? Question 5. Is it true or false? Don't guess though. True. The median and the quartiles are what are called resistant measures. The mean and the standard deviation, on the other hand, are not. So the answer is true. Question 6. Yeah,
So the final's gonna be the same format as this?
no. This is a review guide.
Like, is it gonna be missing from the last chapters or is it gonna be like?
I have a copy of it, but I haven't looked at it yet.
Like, you don't know how many, like, let's say
I can't give you that information, huh?
So you don't know like how many true or false you have, how many.
Oh, I know that. I've told you that before already.
How many questions?
It's 25 true or false, and I think 5 or so free response.
You know, formerly.
Wait, 25 true
I
or
can't bend
false?
down right now, huh?
25 true or false.
I meant multiple choice, not, I'm sorry, not true or false. I meant multiple choice. Yeah.
There's none that are true.
No. No, I'm not gonna give you a question that has a 50-50 chance of guessing. I mean, even multiple choice is already like 25% chance. Even I don't think that's, I mean, if I was designing a test, even I wouldn't give any of those. But you're lucky I'm not designing them. All right, so now number 6. If data on some variable are strongly skewed to the right, then the mean will be much greater than the median, true or false? So they probably want true. It's a general rule that the mean is pulled to the right more than the median, but it's not a universal rule. But they're probably asking for true here, I would say. Yeah.
If it's skewed left, is it? true the same?
What do you mean the same? And the mean is going to be less than the median.
Yeah, like you go like.
Yeah, of course. And it's right and left is just your perception. Question 7.
So the median stays like still on the mean first,
Well, the median moves usually a little bit,
but like.
but not nearly as much as the median because it's a resistant measure. So it's harder to move. Yes.
So the median is if you lined up all the numbers and found the middle, and the mean is the balancing point.
Right.
Okay.
So number 7. Oh, Ariana, how are you?
So why does the
Good.
median tend to be like right under the highest point?
Well, it's only under the highest point if the data is symmetric.
What if it's skewed right or skewed left?
Then the mean will move, median will still move a little bit, just not as much as the mean would. Number 7, if the correlation coefficient is close to +1, then it can be inferred that increases in one quantitative variable cause increases in another quantitative variable. That is false. There's one word in this sentence. One word. I was reading it and I'm thinking true, 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 true. And then I saw one word that changed my answer to false.
Inferred.
No.
It's another.
Huh?
Close to.
One word I said. I didn't, you hit like 9 just now.
Close. Inferred.
Which one?
Increase.
It's two quantitative variables.
Cause. What do we know about correlation?
It doesn't cause association.
Correlation, not causation. One does not cause necessarily the other. They're correlated, they're connected. As one goes up, the other one goes up, not because it causes it, it's an indirect connection. So this one is false. Huh? You do or you don't?
I was saying that was number 7.
That was number 7, yeah. 8. The correlation measures the strength and direction of the linear association between two quantitative variables. That is clearly true. Well, it's like literally the definition. Well, not literally, but number 9. It is difficult to argue a cause and effect type relation from an observational study. However, a randomized comparative experiment can provide good evidence for a cause and effect relation. This is true. Okay, because with a randomized experiment, you get to do controls and treatments. I mean, otherwise, how would the FDA ever approve anything? If you can't infer that this medicine causes cessation of pain or whatever the case may be, then how can they ever approve anything, right? So observational studies, there could always be confounding factors that you can't, take into account, but for a randomized comparative experiment, you can infer causation. All right, that takes us to the end of the first section. Next part. So first, there were 9 questions in the first section. Let's assume to pass that section, you had to get 6 of those 9 correct. Did anyone pass? Honestly?
I didn't have enough time.
To do what?
Like, I don't know, I have to like think before I answer.
Okay. I understand. I get it. There's always the balance between how much time to provide and how much time you have. One of the features of mastery is instant recall and understanding of how to solve a problem versus having to think about how to solve the problem. So, No, so I'm saying, so if you get the right answer, but it took you twice as long as it should have, then on the actual test, you can't just go and, carefree because you're not going to have that time. So that should tell you that, okay, I need a better understanding so I can get to the answer faster. Even though I got to the answer, I have to be able to get there faster. Does that make sense? All right, second page. Problems requiring written solutions. Number 1. The following data are the scores of 22 students on a statistics examination. Part A says, make a stem plot of the data. So I'll give you a couple seconds for this. So I just finished mine. Who here finished theirs in that amount of time? Good.
Stem,
Huh?
the stem part?
The stem plot. Okay, that's about as long as it should take. The way I did it, by the way, is I first did a quick scan of the 22 numbers and saw all the leading numbers, the leading digits. I saw the smallest one was a 5 and the biggest one was a 9. So I did 5, 6, 7, 8, 9 as my stem. And then off to the side, I just put the second digit. So 0 by 7, 5 by 8, 1 by 5, and so on. That was off to the side. And then I went back to the stem plot and put those same numbers in order. Yeah, 100% it does. 100%. 100% it does. Well, it doesn't have to be this way. You can have a stem plot sideways. That doesn't really matter. But the numbers in the leaves have to be lowest to highest. They have to be chronological. Yes?
Professor, there's no, like, let's say for 50, the first number is 51, correct?
Yeah, so
We don't have to put 0 before that?
there's no 50. Why would you put a 0? Right, the first number is 51. So I have 5, 1, 9, 6, 0, 7, 7, 8, 7, 0, 0, 1, 1, 2, 5, 7, 8, 8, 1, 2, 5, 6, 6, 9, 1, 4, 8. What have you guys got? Those who finished it?
Yeah.
Okay. Now, B, find the 5-number summary. What's the first number in the 5-number summary? The minimum, which is 51. Let's do the last number, which is the maximum, which is how much? 98. Then which number do we find next? The median, that's the which one?
73.75.
What do you get again?
73.75.
I get 73.5. It's halfway between 72 and 75. Right, there's 22 data points. So the first 11 and the second 11 split the data in half. So your two numbers in the middle are 72 and 75, and halfway between them should be 73.5. Agreed? Yeah. Now, of the three numbers that we don't have in our table, which one do we just find? The second, the third, or the fourth? The third. We found the middle one. So now what are we going to find? Q1, which is the second entry. Okay, what is it? 68. And what's the last one we want to find? Q3, which is what? 85. Huh? No, ask now, please. Is it about this question? So ask now, please. No, you're here to learn. But
I mean, I said love notion, but like this one's like sounds so dumb.
just ask it.
They're really like, you don't care.
There is a way. There's a way, again, it's time consuming. Like you can put the data into list 1 and then have it ascend it from lowest to highest so that it's easier to make your stem plot.
You don't have to do it.
If you want to make your stem plot, you do.
No, like if I just want to find like the median Q1.
Oh, yeah. You put the data on list 1 and then ask it to find one var stats. It gives you everything. Q1, Q2, Q3, min max. All of them pop out. All right, to be honest, I didn't even think of that because I had the stem plot in front of me. It was faster. Huh? Well, first part's.
Like on the calculator.
No, a frequency list is only if numbers appear more than once and you don't want to have to write numbers multiple times. So you write in the second column how often each number appears. If you leave it blank, it's because you're not using that. There should be no frequency list. All right, C, what's the IQR? 17. How do you find that? Q3 minus Q1, 85 minus 68. And then it says D, use the results to draw a box plot of your data. What would I start my box plot at? Let me rephrase that. What would I start my number line at? What's a good number? 50? And where should I add my number line? 100, 50 to 100, captures all of my data and our nice even numbers.
What if you do a box plot, but you don't do a number line?
Well, the thing is, you want your scale to be correct. So it's always better to draw your number line so your 50, 60, 70, 80, 90, 100 are evenly spaced.
What
So
about,
Well, if the question asks you to infer something and you can't infer it without a number line, then you'll be wrong. So 51, what do I put at 51? Just a dot. What do I put at 73 at 68? A line. What do I put at 73.5? A line. And what do I put at 98? A dot. Any outliers? Any outliers? No outliers. What would the cutoffs be for outliers in this case?
What do you feel about flat on the wall?
Wait, how much on the loan? Oh, yeah, how much? Yeah, okay. How do you get that? Yeah, 1.5 times the IQR is 25.5. Right, the IQR test. You do, the outlier test. You do the IQR, which we just found, you multiply it by 1.5. And then anything past that, you go that far from Q1 and Q3, we don't have anything here. So you should definitely know how to do that. This is a typical, by the way, this is a typical free response question. You're gonna have about 5 of them. So something like this, completely fair game. Which of the 4 sections of your box plot is the smallest?
none.
None?
You
Q1
want to meet.
to the median is, that's why we do the number line, so we can have accuracy. Q1 to the median is like this compared to the other ones, which are all at least 3 times the size. So that 25% is really bunched.
I remember, I don't know if this is true, that each section is 25%.
Each section is 25% of the data, but that section, the 25% is really clustered. It's a very tight 25% versus the other ones, which are not so much. 51, 68, 73.5, 85, 98. Those are my 5 numbers.
So this is Q1.
This is Q1. This is the median. This is Q3. This is the max. And this is the min.
Victor.
Any other questions?
No. Okay. Well, yeah, because I don't know how to do that. I don't like, yeah, I don't
So,
know.
okay, but this is good. Knowing what you need to go over. You have 4 days, right? 4 days would be 96 hours. 96 hours minus 420. That's 91 hours, 40 minutes to go.
Are we gonna have any class Thursday?
Yes. Okay, question 2. The box plots below display final exam scores for all students in 2 different sections of the same course. We have section A and we have section B. A, is it possible to determine the values of the medians of each class? And if so, give them.
Yeah.
What are they?
80.
80. Yeah, what could I possibly say? The line in the middle. Is it possible to determine the values of the means of each class? No. Okay, the 5-number summary is median and IQR. It is not mean and standard deviation. So there's no information that can be provided that way.
So
Yes?
we can't find the mean solely from this box plot,
That's-
but we have the data.
Sure, if you have the data.
You said IQR is only a median.
IQR is only with the median. They go hand in hand. C, give the approximate value of the interquartile range for section A.
80.
45.
No, it's 80.
80. 120 minus 40 is about 80.
Oh, okay, I didn't.
Okay. Now, section B has 40 students. Approximately how many scored above 100? So approximately how many scored above 100? 20, no,
25% 40.
Oh. 10.
10. 25% of the 40, 10. There's 40 students. Each section of the box plot is 25%. So 10, 10, 10, 10. Correct? Questions so far? For 2A? Is it possible to determine the value of the median? It's the line right in the middle. It's 80. I mean, that's what the line represents. It represents the median. Huh? Yes. 3. 25 years ago, a sample of the ages of art objects in the museum had mean 486 years and standard deviation 223 years. If the same particular sample were taken today, what would the mean and standard deviations be? Well, let's give people a couple seconds, but you should have it by now. I mean, this one requires minimal calculation, should take no more than 5 seconds. About what? See, there's multiple things to be confused about when solving a problem, whether it's math or otherwise. You might not understand how to answer the question. You might not even understand the question. That's two different things. Sometimes you understand what the question is, you just don't know how to solve it. But sometimes you don't even know what they're asking for. So do you know what they're asking for? Is that what you're confused about, or how to solve it?
Wait, but if, obviously, I was 25 years ago, but how would you know what the new, like, mean is? Because we don't know how many things they learned. Like,
We don't need to know. The average 25 years ago was 486. Everything is now 25 years older. Just add 25. Right, everything's,
I don't think that's too easy.
it's not too easy. That's exactly how easy everything is, if you know how to answer it. See, in mathematics and science, there's 2 levels of difficulty, easy and impossible. Either you know how to do it or you don't. If you know how to do it, it's easy. And if you don't, it's impossible. Now, questions might take a while to answer. I've done problems that take 20 pages. It's not that they were difficult, it's just that they had, just took a long time to get to the answer, right? So if the average age was 486 25 years ago, the average age is now 25 years more. The spread of ages, how has that changed over the 25 years? Why would it get wider if everything aged exactly the same amount? Why would it get smaller if everything aged exactly the same amount? Huh? It just shifted over. All of your data points shift over, but the spread is exactly the same. So the standard deviation is what? It's still 223. The average went up by 25, but the standard deviation did not change. Does that make sense? Question 4. Is it better to score 80 on a test with a mean of 75 and standard deviation 10? Or to score 70 on a test with a mean of 65 and a standard deviation of 5? Or are they equivalent? Explain and assume both tests have normally distributed scores. Yes, sure.
Yeah, I think it's better to score 70 on test as a mean of 65 than deviation 5.
Why?
Because difference is one standard deviation, which is 5, which we know is 68%, right? Because it's 30.
68% has to do with how many data points are between here and here. That's nothing to do with this problem.
Basically, you're one standard deviation away where the other one is, you're half. of
Okay,
one standard
that's what we're talking.
deviation.
The 68% you don't need, but what you said, but otherwise is perfect. If you score 70 in the second situation, you are one standard deviation above average. If you score 80 in the first case, you're half a deviation above average. Right, your z-scores, if you recall that term. Yes?
How would you standardize this? Like, how would you do the math? for this?
What's the formula for z-score? What's the formula for z-score?
X minus mu divided by the.
Awesome. X minus mu divided by sigma. So 80 minus 75 over 10 is 0.5. 70 minus 65 over 5 is 1.
That's the score?
Those are z-scores. Your z-score is where you are, is how many deviations away you are from the mean.
So you said 80 minus 75 divided by 10.
80 minus 75, the entire thing divided by 10 is 0.5. 70 minus 65, the entire thing divided by 5 is 1. Correct? Okay, 5. Scores on a university exam are normally distributed with a mean of 78 and a standard deviation of 8. A score of 70 or higher is required for a grade of at least C. What percentage of students score below 62? It's an interesting question because that middle sentence does nothing. I don't think it does anything. Hold on. No, I didn't get 5%.
Ooh. 2.5%.
Point 0.0227, yeah. Now they did say using the 68, 95, 99.7 rule. So let's use that rule instead. 62 is how many deviations below 78?
Oh, it's 2, because 70 would be 1.
It's 2 deviations, right? Which means 5%, 2.5%, right? The rule says 2.5% because there's 95% within 2, leaving 5%, but we only want here 2.5%. The exact value was 2.275, whatever, but the rule would state about 2.5%. I don't know why that middle sentence is there because it does nothing for solving the problem. But does that make sense how to solve that one? All right, number 6. It's a good question. It does say using the 68, 95, 99. First of all, it will most likely be multiple choice. In which case you would hopefully not see this. You would just see 2.5%. If I was grading it, I would give credit because it's more exact. I'd probably give credit to both, but I can't promise everyone will do the same because you're not technically following the directions. Number 6, in the setting of the previous problem, find the percentage of students that score above 90. How much? I didn't get that. Above a 90. Yeah, I got 6.68%, about 6.7%, something like that. Yes? What do you do on your calculator? Which button? Normal CDF, lower, upper. Okay, mean. Sigma. Okay, number 7.
What do you got? 0.15?
Now I got 0.0668.
These are the lowest 90, 10, power 99, 78.
Yes.
Spitting out the different number every time.
You have more. It's like you have two things here.
Oh, they stack.
Just do one. Number 7, birth weights at a Los Angeles hospital are normally distributed with a mean of 3,350 grams and a standard deviation of 480 grams. Sketch the distribution of births on the number line below, labeling at least 3 values. What value would I put in the middle? Which is what value? 3350. What would I put 1 to the right? 1 tick mark to the right? Sorry, I couldn't hear. I can't hear everyone. What?
2870.
To the right? I'd be lower.
3,830.
3,830. What would I do to the right of that? 4,310. And if I go 1 to the left of the middle, what would it be? 2,870. And if I go 1 further to the left of that, 2,390. And that represents what percent of my data? No, it's only 2 deviations. 95%. Which means you don't end your graph at those points. There's still 2.5% on each side. So it does keep going. B, the hospital plans set up special observation for the lightest 4%. I thought we did this one. What weight cutoff should be used to separate the lightest 4% of the babies from the others? We did this one already. And do it again, why not? But what's the cutoff? No, that's not the answer. They want to cut off the lightest 4%. What weight cuts off the lightest 4%? What was that?
2,510.
That's what we had from question 1, right? Number seems familiar. Question 8. In a sample of 1,760 hospitals across the country, it was found that the average length of stay for patients under 65 years of age was approximately 6 days. Assuming a normal distribution of length of stay for those under 65 with an SD of 2.8 days, what is the probability that a patient will need to stay 7 or more days? Again, in a sample, N equals 1,760, right? When you read a question, and by the time you get to the end of the question, you've kind of forgotten half of what you read, which happens for the longer ones. What I like to do is start over again. And this time, as I'm reading it, I record all my information. So in a sample of 1,760, N equals 1,760. The average length of stay was approximately 6 days. So X bar equals 6. Or even mu equals 6. A standard deviation was 2.8. So A, what is the probability that a patient will need to stay 7 or more days? Where's that coming from? So tell me what you put in.
7 times the power 99, 6, 2.8.
So you did 7 as your lower, 7 more than 7 days, so 7 or more. You did gazillion, that one, average of 6, average of 1,760, average of 6 and deviation of 2.8. Where do you take into account 1,760?
I don't.
You don't need to get.
Oh, that's this number of hospitals. That's not number of people. Ooh, you're right. That's completely irrelevant information. N equals 1,760. It's not 1,760 data points. It's 1,760 hospitals where we take patients from. Well, we're doing more than 7 days, right? So 7. Gazillion. B, what is the probability that a group of 60 patients will consume a total of 420 or more days of hospital resources? See if you guys can get this one. So now we do have an N. What's N? 60. And if they consume a total of 420 or more days, that means on average, how much? Huh?
Each one stays 7 days.
on average. So essentially what we're looking for is the probability that on average, each one stays 7 days or more. So. All right, let's see who got this one. Anyone? Yes,
Isn't it just,
how much?
36%?
No. That's one person. One person has a 36% chance of staying 7 or more days, but for 60 people to each on average stay 7 or more days is a lot less likely. Okay? Funny bone? Hmm. Been there, done that. Bought 2 t-shirts. So how do I do it? This is a, huh? Sorry, geez. Yes?
You said 136 to the 60th power?
No. No.
What is it, over 65?
No. Yes, but I got. Wow, why would we lower 420? 420 days? That's impossible.
Oh, I made an oops.
You made an oopsies. So remember, there's one and only one change we make when going from one data point to an average. And that is we divide sigma by the square root of n. So the only difference is it's still going to be 7 to infinity. Still going to have a mean of 6. But now sigma is 2.8 over the square root of 60. The only change we make.
He got 0.28%.
Yes.
Where do you go on the calculator?
Same place we did for part A, normal CDF. You're looking for a probability. Where else would you go?
What's your? So lower is 420.
No, the lower is 7. You're looking at the average. 60 people at 420 is on average 7 a day. The average value is 7.
420.
Huh? Nothing's for 420 should not appear in your calculator.
No meat.
0.0028. The lower is 7, the upper is infinity, the mean is still 6, but sigma is no longer 2.8. Now it's 2.8 divided by the square root of 60, which is your sample size. All right, number 9. Which pairs of variables have a negative correlation? Huh? That's what my calculator gives me. I'll go with it. Which pairs of variables have a negative correlation? The weight and height of a student in a Math 140 class. Yes or no? Huh? No, it should have 0. I would assume. Why would weight and height be connected? The age of a child and the number of times it cries each day.
No.
Yeah.
I would think so. As you get older, you cry less, no? Most people. All right, as you get older, you cry less. So yes, yes.
Negative correlation.
As one goes up, the other one tends to go down. The SAT score and the college GPA of a student. No, I would think just the opposite. As one goes up, the other one goes up, or tends to go up. The outside temperature on a given day and the number of sodas sold on campus that day. That's positive. Hotter, more soda. Right? The age of a car and the cost per year for repairs. I would think the older it is, the more it costs, right? Positive again. No, just one. The age of a child and the number of times it cries was negative. The first one was uncorrelated. 10. Suppose that we are interested in studying the relationship between body weight and the percentage of calories consumed as fat for American adults. What is the response variable? What is the explanatory variable? Let's do those first. So let's switch the order. I like explanatory first. What's the explanatory variable? No. Body weight doesn't give you an indication of how many calories of fat you consume, but how many calories of fat you consume should give you an intuition of the weight, right? So the explanatory variable should be the calories. The response is the weight.
What if you make the assumption that people with more weight consume more fat?
That is not an unrealistic assumption, actually. I have a book at home called Why We Get Fat. The book is called Why We Get Fat. And he talks about the fact that, the common belief is that we eat so we get fat. But his premise is we're fat, that's why we eat. It's very, 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 very deep. If you actually look at the statistics during the Depression in the 1920s or 30s, whenever it was, 1/4 of children were fat, even though everyone was poor and there was no money, because what they were eating was crap. So it was all carbohydrates because it was cheap. Anyways, very, very, very interesting read. My ex got it for me. Now I wonder why. Okay, anyway, so if the body weight and the percentage of calories consumed as fat were measured for a sample of 20 American adults, what do you think the scatter plot would look like? Now it says make a sketch, but let's not skip that. What do you think the scatter plot would look like?
Positive correlation.
Yeah, positive correlation, right? We would assume a positive correlation. In fact, part D says in one word, describe the kind of association that's likely, and the answer is positive. 11. The following data represents the yield Y of a chemical reaction at various temperatures X. So you have the first column are your X values. Those are your input values. Your Y are your output values. We have a lot of summary statistics. We have X bar, we have Y bar, we have SX, we have SY, we have R. It says find the equation of the regression line of Y on X. How would I do that? What's the simplest way of finding the regression line? No, the slope is not the line. The slope is the slope. How do I find the line? Y equals mx plus b. How do I find the line? What's the simplest way of finding the line? Put it in the calculator. They gave me everything I need. If I had the formula for the regression line, I could just plug it in, and I do have it. What is it? I think the slope is like R SY over SX, and then the Y. Yeah, you list one, you put your X's, list two, you put your Y's, and you have it compute the linear regression line. You have the formulas too, and oh my God, are those real? Jeez. Anyway, so your biceps. He's like, oh, I was like, this is crazy. Your biceps and my stomach, we'd be comparable. Although the good news is with this back injury that I haven't eaten out at all for the last 10 days, I've actually dropped almost 20 pounds. So that's pretty good.
It's almost like it was a blessing.
But it's not. I'd rather have no pain and be fat. So let's put it that way. Okay. Anyways, find the equation of the regression line. How do I do that? How do I find the regression line? Huh? So we go to list one, stat, edit. List one, let's put it in 150, 150, 160, 180, 200, 200, 225, 250, 250, 280. And then line two, 77.4, 76.7, 78.2, 84.5, 83.9, 83.7, 85.6, 88.9, 90.3, and 94.8. Where do we go now? You tell me. Don't think about it. Stat? Calc? No. LinReg. They want the linear regression line. Go to LinReg. AX plus B. They give me A, they give me B. Huh? Yes. Except for total serenity.
Oh, you should have done that you told me to put away.
Yeah, no, I'm not going to. Huh? You tell me. You just in your calculator. What do you get?
I don't know, I have like A, B, or C.
You have AB and you have Y equals AX plus B. So just plug it in. What do you get? The letter X.
So y equals 0.12, so 0.13 x plus 58.
Yeah. That's it. Now, what yield is predicted for the temperature X equals 190? Without actually doing it, tell me how I would do it. How would I calculate the yield for a temperature when X is 190? You put 190 into X. What is the residual associated with the observation 225, 85.6? How would I calculate that? Yeah.
So, like, y equals AX plus B, and just go with the A.
I'm sorry?
What was the answer for part A?
Y equals AX plus B. They gave you A and B, right? What was A?
0.056.
I think you did the other linear reg. I think you did BX plus A. Or we did something wrong, because that's not what we have.
You get 0.12 for A.
0.13, yeah.
What did you get for B?
58.7, I think it was.
Wait, so for the yield thing, it's 83.4.
I didn't do it. I don't have the answers here.
Just plug in X.
You just plug in X. What's the first line? Read me the first line of your output. Y equals
Oh, you for the formula you?
on your screen. What's the first line? Y equals. You did lit and reg, right?
Yes. it's
So what's the
Y
first line? Y equals
plus B.
AX plus B.
Yeah.
And what's your A?
I got 0.056.
It's- bring it here, please. Please, bring it here, please. Just give it to him so you can bring it here, please. This isn't the screen.
Victor. Oh, yeah.
What the hell do you do? I'm not sure. You didn't even put the data in correct. Your first one should be 77.4.
Mm.
You skipped that number. Your data is wrong.
Okay. Oh, because I put it.
You can't just randomly put numbers with other numbers. They're paired. C, what is the residual associated with the observation 225, 85.6? Tell me how to solve this without actually doing it because I'm too lazy. My back hurts too much. How do I find the residual? Just stop talking, please. How do I find the residual? We have the 0.225, 85.6. How do I find its residual? No. The lows, what?
Like there's no residual like the
Maybe. I need more details. Yes?
Isn't it you find the expected value and then subtract
How do I find the expected value? How do I find the expected value? Walk me through it.
you plug in X value.
What's the X value? Be specific.
2.5.
Okay, you plug in 225 into your equation. That gives you a Y value. The residual is then what? It's the difference between,
Expected and observed.
difference between expected and observed. In a specific order. Right, what is it? Is it observed minus expected or expected minus observed? I think it's observed minus expected. So it's 85.6 minus whatever you get from your computation. Now, the yield is predicted to increase by how much for every 1 degree increase in temperature? This you can answer. How much? Units, please. Do we have units here? No, it doesn't really give units. Maybe it's percentages. Probably percent. So remember what the slope represents. The slope represents how much y goes up for every 1 unit increase in x. So if the degree goes up by 1, then y goes up by the slope, which is 0.126. 1261, probably percent. Because a yield is usually a percent. What? You don't find it. It's the slope. 0.126. Which is what? Which is A. Oh, I see what you're saying. Yes, which is A. I think it's percent. I mean, there's no units given, but the yield is probably assumed to be a percent. All right, number 12, last one for today. And just so you know, we finished 5 pages of this packet and it's a 31-page packet. So unless the answers are at the end and it's, oh, there's a lot of stuff here. There's tables at the end and there's answers at the end. Oh, okay, good. So there's only, well, this is a great place to start. And then if you get a bunch wrong from a section, I would certainly spend extra time on that section. Oh, it's only 18 pages, but we only did 5, which means we're not going to finish next time. But nevertheless, if you get through 11 or 12 pages, it's still pretty good. So question 12. A statistics instructor does a linear regression of final exam scores versus midterm scores for the 32 students in his class. The correlation R is 0.8. The regression equation is final equals 10 plus 0.9 times the midterm. So your final score is your Y value, your midterm score is your X value. One student, Mary, got a 90 on the midterm. What is her predicted final score if she got a 90 on the midterm? Which is what? She got a 90 and she's getting an 18.1 on the final? 91. 90. What do you get there? 91. 10 plus 0.9 times 90. In fact, Mary's final exam score was 98. So what was her residual? 7. She got 7 more than her expected. What percent of the variation in final exam scores is explained by the linear relation to the midterm scores? Huh? How much? No. 64%. Where does 64% come from? No reference to standard deviation anywhere in this problem. You square R, it's the R squared. If R is 0.8, R squared is 0.64. 64% of the variation in final exam scores is explained by the linear relation to midterm scores. The rest of it is explained by other things like, I don't know, studying, and just maybe some of the questions asked happen to be things that you knew, and as opposed to not. It's luck, yes. Sure. Just plug 90 into the formula. I don't understand. It's 10 plus 0.9 times 90. 91, yes. 10 plus 0.9 times 90? No, no, stop right now. You didn't add before multiplying. Order of operations, that's like 7th grade. No, it did not. Do it right now. 10 plus 0.9 times 90. Yeah. Residuals is observed minus expected. All right, I will see you all on Thursday.